Hello everyone, today I am going to be talking about one of the huge drawbacks of helicopters compared to airplanes and what this might mean for flying car concepts. But first of all, I am always open for topic suggestions, and I have several ideas right now, including the wider thematic of flying cars, the potential future of dinosaur and similar re-entry glider concepts, the problematic of hypersonic travel, basic orbital mechanics, and maybe debunking some of the more completely crazy ideas that sadly seem to be taken kind of serious throughout the internet. Uh, so, any feedback on which kinds of topics you would find more interesting or any suggestions would always be welcomed. But now, on to the actual topic of this video. Now, there are many differences, of course, between helicopters and airplanes, and among others is speed, but also efficiency. The way an airplane sustains flight is much more energy efficient than a helicopter, and you have to somewhat simplify, but you don't actually have to simplify it that much to make it quite obvious why. That is, if you look at a helicopter when it is hovering, it simply just pushes air down through its rotor at a certain speed, and it only sucks in air at that speed as well, whereas in fast forward flight, a helicopter can actually become more efficient and need less energy to just sustain altitude, but it's still less efficient than an airplane, and that's because an airplane, while the aerodynamics around the actual wing of an airplane are quite complicated, just in terms of outside energetics, it's more efficient because it gets a bigger stream of air, and the direction in which the air is essentially delivered towards the airplane is perpendicular to the lift the airplane needs to sustain flight. So, if you look at a helicopter, it needs to speed up air to a certain speed in order to sustain flight, and it also needs that speed to suck in enough air, and thus the force that is lift that keeps the helicopter up has to be delivered in a certain speed, which then multiplies up to power and thus fuel consumption. And when flying forward, the rotor disc gets kind of it tilts forward, and the airstream actually gets kind of curved into that rotor disc, but so it can take in more air since as it travels forward, but it still gets much less air than many airplane designs, whereas the aerodynamic effects of the wing actually stretch far above and below the wing itself, and thus there is, as you can see, this rather big amount of air that is manipulated by the wing, and since you have more mass that is essentially deflected downwards, you need less velocity change to get the same force and the same lift. So the air ends up getting pushed down at a lower speed, which essentially means that you need less power for the same lift. Now, this is quite simplified because the internal aerodynamics of how the wing or the rotor actually works are taken out, but this means that just from the get-go, just from the outside energetics, an airplane is much more efficient than a helicopter, and in fact the aerodynamics, while they're much more complicated for a helicopter than for an airplane, the rough efficiency values are pretty much the same because rotor blades kind of resemble airplane wings, and such an airplane can reach much bigger fuel mileages. Now, this is kind of important. If you look at tilt rotors, for example, like the V-22 Osprey, one of the big advantages over normal helicopters is not just that it can go faster, but also that it has a much wider range. And as a rough rule of thumb, you can say that an airplane and a helicopter with a similar size to weight ratio and a similar fuel capacity to weight ratio and a similar design idea, like if you think they're both designed to be efficient, of course, then the airplane roughly will have about 10 times the fuel mileage of the helicopter. And of course this rule is just a rough estimate, and of course it doesn't hold up for special cases. Of course a jet fighter with engaged afterburner has a much lower fuel mileage than an airliner, but as a rough rule of thumb, you can say that airplanes are about 10 times as efficient at long-range transportation, which of course is also important for flying cars, because if you think of flying cars, or generally cars, for people who to commonly buy them and fly around in them, assumably, then fuel mileage is, after all, kind of important stat for a car or any personal vehicle. And a very well designed flying car with a wing surface that essentially works like an airplane could potentially reach fuel mileages, or actually in case of an electric vehicle, there are different ways to convert the electric power usage to fuel consumption. You can use the efficiency of the engines and the actual energy contents of the fuel. But as a rough estimate that also is very practical, you can kind of compare the fuel prices to the electricity cost, and if you do that, you can come out that a flying car, that it's actually quite similar. A flying car using a combustion engine or a flying car using an electric engine, if very well designed, both could come down to a cost equivalent of about 5 liters over 100 kilometers, which is kind of good-ish for a car, and it's not easy, but it's kind of achievable if you design a flying car very, very well. Whereas a pure vertical flying car, which basically resembles a helicopter or multicopter, which often are commonly misnamed as drones, which is not quite correct. The word drone simply implies any unmanned vehicle, whereas what people oftentimes mean when they say drone is actually a multicopter, that is a vehicle that essentially works like a helicopter but has multiple rotors, usually in some kind of axial symmetry around the main fuselage, so a quadricopter or octocopter. Those would be roughly 10 times less efficient. If they're very well designed, maybe only 5 times less efficient, but still they would be very expensive to operate, even if the vehicle itself would be less expensive. Now, of course, an airplane-based flying car design has the drawback of needing a runway, but there are actually several designs that would incorporate the basic VTOL idea of having like a tilt engine or several engines, so that the vehicle can take off and land vertically, but then travel a long distance like an airplane by either tilting its engines or its rotors, like the V-22 Osprey, or having several engines, that is basically having like 2 rotors, for example, and then in addition 1 propeller at the back. And this way you can kind of combine the efficiency of an airplane and the capability of vertical landing and takeoff from a helicopter, and I think this is widely underrated among people who don't really think much about the basic physics and principles of aviation, that this is actually kind of a necessity for any flying car concept to actually take off. Uh, there are a few concepts that use that, and I think these are pretty much the only concepts for flying cars that actually have any chance of commercially taking off, because any flying car that is just a multicopter will basically be just a toy. It can be used to fly around a few times and have fun, but if you really want to use it to go somewhere, then it's just extremely inefficient. You have to keep in mind helicopters, for example, while they do get up to ranges that would be generally accepted on the car market, they also eat a lot of fuel. Many helicopters have a fuel capacity so that the fuel you can put in them essentially weighs as much or a significant portion of the whole helicopter. An average business helicopter can fly as far as would be an accepted range for a commercial car, but the problem is that just fueling at full costs about as much as a small car. So it's not really an acceptable solution for the average consumer. So I really only see a future for the tilt engine flying car concepts. I hope you found this kind of interesting, and thanks for watching.